So I went to KTH here in Stockholm, did computer science there, and I know a lot about runtimes and operating systems since I got into it early. We did our own JVM called JRocket, which is a semi-famous old Stockholm startup called Appeal Virtual Machines that was bought by BEA, that was bought by Oracle. So that way I got into the JVM game after working as a performance consultant with Java, and a Java consultant really early in the game, mid-90s. I know a lot about low-level stuff, so ask me questions about it if you want to know about it. I'll start at Klarna in 2 weeks. I tried to have the summer off, but I've been unsuccessful. I think I've been working every day since I quit Oracle. So 2 more weeks. Next week my wife is gone, so that's going to be horrible. But the week after that, I will be incommunicado with the world and try to have a vacation for the first time in 3 years. So, agenda for today. We're going to talk about robustness in commercial apps and special apps. Another thing you have at Klarna, which I think is a luxury, is that you have sort of internal releases of your services. You don't have to communicate to the world that in 6 months on this date we will release Java 9, and if we're late, we have to 3 months in advance say that and take a lot of pain. You have internal releases, whereas we have to be ready with a certain quality at a certain test schedule in the productization world like that. I'm going to talk about build systems, source control and development, and testing, especially testing of performance, which is an often an area that people don't give as much attention as it deserves. How to store these results, build a healthy test system, automation, complex and not so standard testing. What do you do if you have a crash dump that happens once after 3 weeks in production in some Japanese bank who yells at you? How can you make a commercial product more robust like this? Development processes and the battle scar story. My favorite one is, of course, acquiring Sun Microsystems, which I now can talk a little bit more freely about. So I know my stuff about low-level systems and JVMs and runtimes and Java. I also spent 4 years on an operating system project doing a hypervisor-only virtualized operating system that would run Java, and there's a lot of strange stuff that crops up at that kind of level. Runtimes in general are harder to debug. Software hardly exists because stuff is tightly coupled. You have a garbage collector interfacing with thread roots, interfacing with the code generator, marking the thread roots that these are objects, these are to be collected, and all the subsystems talk to each other in many ways, not all of them API friendly. You have an operating system like behavior. A JVM is basically an operating system for running Java or a Java language or Scala or something that's compiled to bytecode. And this puts extreme demands on the testing infrastructure you have to maintain robustness. So we started out doing a JVM in '98. In a company called Appeal Software Solutions that was a Java consulting shop in Stockholm. And the reason we did this was that Sun were delaying Hotspot, and our customers who were starting deploying the earliest Java EE applications noticed that the Sun Classic VM didn't scale at all, like native solutions. That's much faster than Java at this point in time. So we figured that Hotspot would be an adaptive runtime. It would solve these problems. It had all these old self guys aboard and all the gurus. But 2 years in a row at Java 1, they had the exact same presentation that said, soon, Java will be really fast soon. So the second year in a row, in '98, when we heard this presentation, we decided that we can't wait any longer. I mean, how hard can it be? Let's build our own JVM, and our customers will be happy. It's going to take 6 months, and we'll be up and rolling with fast thread systems and scalability, right? So this is a 700-page book that I wrote together with a coworker of mine about JVM internals. So if you're interested in JVM internals, and not just those of our JVM, Oracle JRocket, which is gradually being fused into the Hotspot OpenJDK. Anyway, if you're interested in JVM internals, it turns out it's like an 800-page book in there, and not just something you do in 6 months. So throughout the years, with funding on this, I gathered some experience in complex systems. And it's a strange beast. Even though testing and continuous deployment and things like this weren't standard word-of-mouth things, at the end of the '90s, we had to invent a lot of testing methodologies from day one. Or, okay, maybe from after a year or so, we realized what we needed to do and what we couldn't test and what we had to do. So we made many mistakes along the way throughout many years, testing these kinds of complex systems that also go out to customers that ship on tight deadlines that you can't really skip. So we had to invent a couple of new ways to test tightly coupled systems. And we also have sort of a vision of what a QA utopia would look like, where you can always spin off new bits. This is product, I press the button, ship it. I mean, that's QA utopia. That's never going to happen to anyone, but we sort of know how some of the obstacles on the way there would look like. Most important lesson is I think that QA infrastructure and testing is harder than development infrastructure. It's actually more important. You have to do it right, you have to do it from the start, and you have to develop it parallel to the application. You can't just come after like 6 months of proof of concept hacking and like, wow, this almost turned into a product, the customer wants it tomorrow, let's see how we can test this. But everyone knows this today. Not everyone knew this in the 90s. Not everyone does this today. So this is not necessarily test-driven development. It's not necessarily like, there's a lot of rituals in Agile. Like Agile is a good thing in the classical sense of the term, but it's also opened the door to a lot of these flip book charlatans who come in and like put up flannel boards on your walls and force you to every day move these little flannel signs. That's not Agile at all, but that's like, it's a ritual that's coming in there, and that's the same way you have to be a little bit wary about TDD. You can't like write garbage collector tests before you write the garbage collector and so on. So don't adhere strictly to the ritual, but be Agile. And sometimes the boundaries between the app and the test infrastructure aren't even clear. Sometimes you have to export a test from the app in an API that no customer would use just to be able to test it, white box testing. QA and dev roles, and Dan was on this as well. QA should not be a separate department on another continent considered as testing grunts, which is a very American mindset that at least like way into the 90s, you hire some QA guys. They don't need a computer science degree. They don't sit and click stuff. They don't need to know how the product works. So that's completely wrong. When it comes to working QA, they have to be on the same dev team as the developers. They have to be able to do the developer's job even, I would argue. They would just be different developers with like the quality responsibility for the product. And we should be able to, as devs, replace the QA, and they should be able to replace us for small projects. Preferably physically close, not even on a different floor, in the same room, on the same team. That is my experience. So it's very dangerous to wall off a QA department. And when I managed to sell this idea, like bring in QA guys to all the development teams in our VM development center, management took credit for it quickly, so I know it was a good one. So it's very dangerous, again, for QA just to do black box testing without understanding what's in the box. One example from Sun Microsystems is that they were running hundreds of JVM tests for thousands of CPU hours every night with all the different garbage collector flags available to the hotspot virtual machine. And none of the tests were ever garbage collecting anything or allocating memory. That's what happens when you just do black box testing and have your QA on another continent. So in my ideal team, there's no difference between a developer and a QA engineer. Do not treat them differently. Do not denigrate the QA engineer. He's at least as valuable as the dev, perhaps more. They have different skill sets, but they overlap a lot, and both are extremely skilled positions. Like these sweatshops in low-wage paying countries where they hire QA consultants to click on stuff, that makes me sick. That's not QA. Something else. So, build system basics. Build systems are important for any kind of service, any kind of thing you build, even a JVM that just turns into a DLL and some fluff around it. You need a build system, a test system, and a source control, and no one, again, 2015, argues that they shouldn't be the parts of the same system. Source control tests should be checked in with the product, like that's the Maven project model, that's the any project model. You should have some kind of distributed system, like Jenkins and QA machines and customized clusters that do your testing around, and you should know how to talk to that system. We found it very useful to have mobility clusters way before anyone had invented something like Jenkins, so we could build anything locally or globally. We had a distributed cross-compiler running out in our QA cloud. So I could say, give me all the bits for all the platforms, even though I'm just on Windows x86, like, and the remote system would upload my bits before I committed anything, or before I committed anything to production or a repo or anything, and just build those to make sure they worked on all machines and give them back to me very quickly. Very useful feature, distributed cross-compiler. Self-contained and part of source control, so basically we have build kits, which say that this compiler, we know that works. If you build something as complex as an operating system with the wrong C compiler, you will have compiler bugs and something subtle will break, so we had to certify and test compilers as well. So we have build kits, which was like, take a clean machine, nothing on it, sync out a repo of the JVM with the operating system or like the product you're working on and type make, and the first thing that would happen is that the build kit would be downloaded, the ideal compilers that you know work, the tools you need to build. Do the same on a different laptop, same hardware, identical bits would be produced. And Virgin laptops should give you the same bits, then you're doing it right. That's a very healthy way of approaching builds of complex systems. Tests, also under source control, not controversial today at all. Virtualization is another boon to testing because back in the day we used to have physical test machines. They would run at 5% capacity where they're running functionality tests, and that would be it. And there would be queues waiting to run these functionality tests on this platform. Now you can run just as easily 30 machines that do the same easy functionality tests on the same hardware with virtualization, maximize resources. It should be able to test run locally, so you don't bother anyone else. It should be able to test remotely using the build system for your builds. There's plenty of commercial products like this today, but it still pays off to customize them so you can do things like this easily. When it comes to test machines, the only dedicated machines that you really need in this virtualized world we're living in right now are performance test machines, because performance is a finicky beast, and if you're running two virtual machines on one computer, you will get completely different performance results, even though they're isolated from each other. So that makes sense that it's hardware and physical hardware you're running on. When it comes to functionality tests, just virtualize the heck out of everything and make available as many machine images as you need. And we also had it before, like we had enough hardware to run that any developer machine could also volunteer a number of cycles for testing, and you would run tests locally to get all these remote tests run and get back to you, which was handy. Unless you were running benchmarks and forgot to disable it, because then it sucked. So any test cluster, it should be easy to add new machines. Again, virtualization is extremely easy to add new machines, but here's new physical hardware, register it into the build system, and it will be there. And I've said it several times already, but virtualization for this is lovely. So any complex test environment, even performance testing, setting up something like an app server test that tests like JVM performance and load throughput and things, you can virtualize that. You can do the 2-hour setup you need to create these like two virtual machines that need to communicate. Then you snapshot these virtual machines, and then you never have to set it up again. So in that way, you can actually do performance and load testing and things like that using virtualization by like, okay, I broke something in the configuration file, I don't care, restore the image, here is my complex test setup again. And this is a work saver of like orders of magnitude of anything that existed before. So there are performance problems with virtualization or performance artifacts with hypervisors, but the way that you can have these complex sets up and reuse them when you change the system is a very useful thing. So when it comes to tests, you have regression tests, of course. You have regression tests both for functionality, which is what I will talk about first, common practice, and regression tests for performance, which are a bit harder. The simplest regression test that you have, you find a bug, you have a reproducer, you whittle it down to some little program with a main function and the return value, which is true or false, or a JUnit test, or whatever you use. You keep it simple. So if you spend a few hours, like this is very typical in complex systems, you have some crash, but it's still deterministic if you can find out why it's deterministic. So you spend a few hours whittling down this huge program that the customer had that sometimes crashed to this small program that crashes 100% of the time for a certain bug report. And I would claim here that if it's simple to submit such a test, once you have that reproducer, if you could just like put it in the test system now, it will forever be there. 50%-ish of bugs that can get regression tests added as part of the original bug fix, or can get that in this kind of environment. So never ever check in a bug fix without the regression test unless it's hard. Again, rituals, if you cannot do a regression test for something but still are 100% sure of why it happened and that you fixed the bug, again, your ritual shouldn't like allow you to get into the way. You should tag your bug with that and provide a description. But frequently there have been problems with this in various commercial setups. Like you sit there with your reproducer after having solved the problem, and you hand it to QA on another continent, and maybe they will check it into their code base in a few months, or they'll forget about it, or they'll run it with different flags or whatever. So the developer can do this with a push of the button, and I mean, it should be a no-brainer. Make it so. So not all tests are reproducible by a simple JUnit tester main function, so I'll address the other parts later. I'll just talk a little bit about the results database. I'll stray a little bit in utopia here. We did some of these things, visualized some of these things, and then the operating system product that we did, which was called JRocket Virtual Edition, we did some more of these things. But basically, log and save everything. Every crash, every failure, everything that happens in production that you have like phone home callbacks enabled on. I understand that you don't have it at your customers, but if you're dogfooding your own org, for instance, save everything, save every test result, save every build result, grab a MySQL database, get it up and running, hack these things quickly, get it up and running. Like, it's as equally important to get QA up and running from day one as to get your result database up and running from day one. So, an ideal result database, you come from your local machine, ask the QA system, when exactly did this performance regression appear? And you would get like a list of performance numbers, performance runs with standard deviations. List all benchmark scores on this machine in the distributed test park since January 1st. Has this functional test failed before? What were the bug fixes? Some of this is done today with like awesome productivity tools like Crucible. It shows that linking issues to source code access is really a productivity enhancing thing when it comes to QA, but also custom solutions might be needed. Distributed code reviews is another thing that this kind of thing enables, looking at the issue directly and adding comments. Just having mailing lists for code reviews when you're a distributed org might not be so good, because usually it ends up with like a lot of ego saying, oh, I don't like the name of that variable. Look, I did an action item when you send in a code review to a mailing list. So it's better to have some kind of productivity tools in check to do this. Again, avoid the rituals. Don't demand that everyone has to find a fault with a code review just because it's there. Performance is the hard part. It's because anything and everything can affect performance. Moon phase virtualization, power fluctuations, the wrong incantations, someone switching off the more magic switch in the server room. So for performance regression tests, you need automatic regression warnings. If something gets slower, the test system should raise the alarm. And it's also hard because something gets slower. How big is the standard deviation? You sort of have to know your tests. So there is a lot of manual effort laying the groundwork for this. And there are false positives, which you have to avoid. And you can't really never do that. But you can analyze that if you have a good result database that you can interact well with. And make it easy to continuously add more benchmarks again here. And I say automate. Automation is better than no automation, even if Dan said that automation can also get you stuck in traps, but so can everything. So good result database performance has baselines, deviations, and invariants, and you can see things if a deviation has grown, but is still in like the interval it was before. So performance testing, if you can, do a lot of continuous automatic performance testing. And even functionality testing, actually. Functionality testing as well, because one thing that I learned from my 20 years or so in the industry is that bit rot happens immediately. If you support several platforms, and not, again, a luxury you don't, like you have in a place like Klarna, is that you have a service and you deploy it on the same architecture, and it's up and running, and you can ship it when you want, when it's ready. Well, truth and modification, but it's a very different world to like shipping customer software for 5 different silicons and 8 different operating systems every quarter. So one thing we did before we acquired Sun was that we had on and off support for Solaris as an operating system as part of the testing. And when we didn't have support to save cycles and reuse those machines, we switched off Solaris testing, and it would that would break in 2 weeks, even if no one was writing Solaris code. People were just writing platform-independent code, and they still you looked away and Solaris broke as soon as you said testing off. So this is a very important lesson about bit rot. Every cycle, use every cycle, and if you ever plan to have that version again, it might be easier to build it from scratch if you just skip testing for it for 6 months, because things will have changed and it's going to be hell to untangle every time. So what we also know is that the release version and the debug version may break each other because C compilers and different platforms, something might work very well in debug. Compiler optimization comes in release, and suddenly the new code you wrote doesn't compile because there's a bug in GCC or something. You can write what you think is platform-independent code for POSIX systems, and they will work on Linux, but not on Solaris. You're just sitting there with a Linux machine, so you have to be able to test on Solaris before you submit the entire 300-person global team to your Solaris bug that you didn't even know you wrote just by changing some POSIX code. So we have things like local tests, which would, like for my platform, distributed build system, build for my platform, give me back the code and run like large parts of the functionality and regression test suite on this machine and compare it to previous results on this machine in the result database. And remote tests basically do the same thing, but for all operating systems and platforms that we are currently supporting. So before I commit any code, I do a remote test. The remote build system will build me binaries for all the like 15 different configurations that we have to ship for, and it will send these binaries out into the cloud and run them on these systems. And I will get extensive logs, and I can analyze them by querying the result database should something be wrong. It's actually more common, I think, that I break Solaris by mucking around with Linux than just like by working on Solaris, weirdly enough. Joel has been in support, so he knows what I'm talking about. I think I've been the source of much of your pain 2008 through 2010, actually. Fair amount. And the other thing that I can say if you work on multiple platforms is that you have to be ultra pedantic with the compiler flags, because compilers compile different code for different platforms, different binaries for different platforms. Never ignore warnings. First thing that happened when I tried to build the OpenJDK after you acquired Sun was that I had like 13,000 warnings or something on a standard Linux box, and they had been living with this for 10 years. It was normal to them. And never ignore a warning. A warning is an error. We are moving to that in the OpenJDK only now, and it's going to be great. If it's problematic with something that doesn't work across different platforms, it might be best to avoid it. This is also like hard sometimes because like standard C++ STL classes aren't still used in the OpenJDK because the Solaris compiler is retarded. So I mean, it might set you back, but sometimes you need to make these kind of trade-offs. So warnings are errors, and if someone checks in a warning or it gets past the testing system, I mean, the truncheon is the only appropriate response. Maintain code hygiene. So, if the test fails, what's the command line reproducer? For simple functionality tests, this is one that I've spent wasted hours on, days, weeks, over the years. So I asked the QA, what's the command line reproducer? I saw I had this nightly failure on this test, but I can't figure out how it was run. Seriously, just give me the command line reproducer, because I wrote this test and it was a main function that returned true or false. How do I run it? How was it run? I'm like, no, I don't want that huge log with Maven running something in the background and 250 environment variables. I want to know how to run this from the command line, because when I wrote this was a command line test. Just tell me the machine, just tell me what like flags there was. And QA departments, if they're not in the same room, they will not understand that you have a use case as a developer. It's like, I want a command line reproducer so I can see how this test failed. And this is the saddest of all QA stories I have for you today. So make sure that that is easy to see. Of course, now we talked about simple regression tests, main functions, and JUnits, and I claimed that it was almost 50% of all the tests if it's done correctly and simply, but there's another 50% in the world, especially in operating systems and runtimes. So, simple programs with main functions, don't cut it, of course, for everything. I'll give you some JVM examples. How would you test that the JIT compiler in the JVM has a specific optimization that runs on code sometimes? That works. How do you test it works? You think it works, you write unit tests for it, you ship it, and some customer, probably a Japanese bank again, will come back to you after hours in production with a core file and say that it failed. And all you can see is that it failed somewhere when it was optimizing code on the intermediate representation that we use internally. And heroes like our last line of support will extract at least the intermediate representation from this huge core file that happened once for you. And you can whittle it down, and it's still huge. It's not human readable, but you know something broke. You can't really see where. So, again, same Japanese bank. 48 hours in production, the garbage collector crashes because heap objects happen to be just so on this address. This is some boundary case that we've never seen, because how do you unit test the garbage collector? The heap has a virtually infinite amount of inputs. So the key observation here is white box testing. We need to be able to export a state. And in the case of the IR here, which is like too large to read, if you can inject it back, you can see on the stack trace in the core file which optimization broke. If you can inject this back into the VM, have it execute just that optimization and break the same way, you've gotten a lot closer to reproducible for something that seemed impossible to reproduce. So if you can inject things back that you can extract this way, you have an even more robust QA infrastructure. So for the garbage collector, you can create an artificial heap or get the heap from the core, or compact it or whatever, compress it, put a few objects in the nasty places. If you sort of understand what happened, inject this in the runtime, trigger garbage collection, and if it no longer crashes, you sort of have a regression test for this thing that you've only seen once. Same thing, as I said, serialize the IR before an optimization that breaks, inject it back into the JIT compiler in the runtime, trigger the optimization. The system doesn't need to be up. It can be running on a heart-lung machine, artificial breathing. You just have to have enough state to run this optimization and see that it doesn't crash. Then you can throw the machine away, the virtual machine away, and you sort of have a unit test for something that seemed very hard or impossible to unit test and was very hard to reproduce. So you should modularize your application enough to enable white box testing, which means like adding APIs that the customer doesn't see but are still there that you can use internally. And it's never as simple as that. Because you have parallelism, you have multi-threaded apps, you have race conditions, you have things that you can't figure out what they are because they depend on the parallel state. How do you even make test cases for something that can or cannot be a race? NASA has like synchronization points in their code base that certain things have to be correct. They run static analyzers on the code, and if you can't statically analyze the code, you can't send it into space. Fair enough, I'm not going to send my code into space, but I still want to make sure it's parallel safe, thread safe in some ways. You can sort of randomize inputs, you can randomize sleep times, you can mess around with thread scheduling, try to cover the malicious side effects of parallelism by crunching and changing a lot of stuff in the timing in the system. And for the programmers, you at Klarna, who have it so easy and the luxury and et cetera, you're moving to a world full of implicit parallelism. We're doing map reduces these days, we're doing streams in Java, we're doing Lambda, so we don't have to create threads and synchronize and wait notify between them anymore, which is good because no human can really do that very well. So in order to stabilize and make something like this robust, you have to add a pinch of terror testing. This is not scientifically accurate will get the reproducer in any way, but before, you have to harden a product by exposing it to a hostile environment. So a Java virtual machine, you're typically hardening it by running a lot of stuff for a long time, complex app server loads and things, by allocating much more objects than you would do in separate threads. You redefine a lot of classes because the JVM hates that, and the system dictionary is a global lock and things like that. The operating system, you toggle back in between user and synchronized mode, changing rings when you shouldn't have to make sure that you don't break any privileges. Throwing exception from static initializers in Java is one of these horrible things, because Java class initialization, people who work on the Java language team like me know that it's a short story, but it's quite a long short story, how to initialize a class, in which order things happen, and if exceptions occur along the way. So just an exception from like a static curly brace block. Do that a lot in different threads. That'll confuse the hell out of the JVM. De-optimize a lot. You JIT a lot of code. Some assumption goes wrong. Typically what the OpenJDK machine hotspot does, it goes back to the bytecode interpreter for that code from where it was, on stack, replacing states with interpreter frames, which is completely horrible to get right. Completely unreadable code. Almost as unreadable as the registry allocator in hotspot. But if you do this, this is one of the terror tests that Oracle does, de-optimize a lot to make sure that we can handle these transitions, because they also tend to create these very rare states where suddenly something is broken. And we have like a system called Kitchen Sink that does this terror testing, and I think commercial releases have to harden for at least 2 weeks without bugs on all platforms in Kitchen Sink, so that's good. And sometimes you just need to crunch for a long time. Nothing else suffices to reproduce a problem. And the framework, white box testing, if you have like this great white box testing framework, you can't test for everything because it's highs and bugs and you add overhead or something breaks. So use all free cycles in your machine park all the time and crunch if you don't use the machines for anything else, like run some terror testing. Make dumps when they happen, full and comprehensible. And, as I was alluding to in the beginning, disk is cheap these days. Save everything, always. Even if you have like a 3 gig core file that appeared once, save it. Because when I get that bug in 7 days and look at it, and I find out that you wipe your hard drives after 6 days because of space requirements, I'm going to be mad. And I'm never going to see that bug again. So save everything. And also, if you save this bug and the stack trace, and you see a similar bug, it can correlate the stack trace automatically, and you can see that this seems to be the same issue on 2 different machines, and it'll give you huge amounts of more information. So something we did at Oracle, or BA rather, before Oracle, was to inflict callback code called phone home on the entire org who used to dogfood our VMs before they went out, which they hated because they tended to be unstable and crash the first part of the stabilization period. But every morning, when I came to work in Stockholm after the US had a frustrating work day, I would have like not one dump that happened once and we never saw what it came from, but like 6 dumps with the same stack trace on different machines, and I would immediately be able to deduce where the problem was. So collect all the data. Platform matrix. Minimize the amount of common code. Sure, you can write POSIX code on Linux, it breaks Solaris, but still, it's a choice between platform-specific features and test matrix growth, and also minimize parallel code bases. One weird thing we did in JRocket was that we generated the stub code, the assembly code that goes from Java to C code, which is different on all platforms, platform independently, and fed it to our own code generator. So we only had to write it once. That was cool. I have a patent for that. Hotspot has 2 compilers, 2 JIT compilers. One fast compiler that produces sloppy code, which is called C1, just so the system can get up and running fast, and one called C2 that produces worse code. It's slower, but produces better code. And we have to implement every new feature in 2 places, once in C1 and once in C2. And if the test system that night happens to run C1 in the new feature and there's a crash there, a bug there, it will crash. Otherwise, it won't. So try to keep one code line alive. Tier it if you must, but don't spread it away. False abstraction, that's like, yeah, it's platform independent, but this function takes an extra parameter, and it's always null on Solaris. That's not platform independent code, that's something else. So be wary of the platform independent thing. Development in reality, don't be too much of a quality fascist when code is written. Code must be written quickly and mercilessly sometimes. If you spend all your time preventing larger check-ins or have like rituals with flannel boards and code reviews, you might be in trouble, but I mean, it's necessary and good to have this, but it's more important that the infrastructure very quickly and mercilessly raises the alarm if something breaks. That way you can maintain agility, not live in a tightly regulated, non-agile world as a developer or a QA person, but you can still prevent further damage if this happens, and never promote broken bits. So I'm going to sum up with a horror story and a what did you learn today thingy. So the lessons I tried to impose today was to build a test infrastructure in parallel with the application. I don't think that's controversial at all in 2015. It was 20 years ago. TDD and other religions might not be the whole answer. You need to be agile in the true sense of the word agile. If you demand that you write a test for a feature before you write the feature, you're just going to have unhappy developers, and it's not always possible. But everything in moderation, sometimes it's a good model, sometimes it's not, and the team should be senior enough to understand this and communicate about this. There's no boundary between QA and dev work. Keep them together, preferably in the same room. Do not separate them. Do not think of them as different other things than different aspects of the same role. Think about white box testing all the time. There was no white box testing in the Hotspot JVM when we acquired Sun. Micke, one of our GC guys, wrote a white box testing framework, and they just like looked at him as he'd grown a tentacle from his forehead and didn't understand what he was talking about. So there was some QA issues in that organization when we came in. And if a system requires tight coupling, which some of them do, don't be afraid to do that, but think about how to do that. And make it easy to add and write tests, that's saying itself. And use all available CPU cycles for testing in the cloud. 4 minutes left, so I will just summarize with my little acquiring Sun horror story. versions of this may vary, but as you know, Oracle bought BEA, where we came from, with our VM in 2008, and Sun in 2010, when Sun was going bankrupt. And I think there's a happy ending to the story. It's certainly become less scary, much less scary, but there are sequels to follow before we can get to the Hollywood ending, I think. So Sun was acquired by Oracle in 2010, and it was decided that we should use the Sun code base, which was already in the OpenJDK for the JVM development. And we had spent like a year just modularizing and preparing stuff, taking to heart all the stuff I've talked about and making it so testable and nice and modular and platform independent that we could. And Sun had basically spent the last 4 years trying not to die financially, betting the company on Java FX, firing American QA because Silicon Valley salaries really mattered in the balance sheet because they had that little money, hired new QA in other countries, hadn't seen the product before, didn't understand what they would test because they didn't have the feeling for the product. They had no code standard in the code base. Curly braces could be anywhere. They could be optional in one method in five places. Sometimes they would be there, sometimes they wouldn't. Sometimes return statements would be on one line, sometimes it would be on the next. So it's really hard to like, just give me one code standard and I can read the code, but don't give me 5 in one method. And this is still, if you read the OpenJDK, it's not as much as a problem in the Java code base as it's in the VM code base, but I hope this will be sorted. It's very hard to change this without having really disruptive changes. So the org was very shell-shocked after the traumatic state of Sun, and they had nothing like build kits. You had to go on a wiki page and see which 15 components you had to download from the internet to build a binary today for Solaris. Obviously, that was not very testable. You might even not be able to repeat the bug because someone used a different compiler. They couldn't use, they didn't have any Windows development at all, even though they built Windows versions. They didn't use, as a rule, IDEs in this org at all. They were sitting there in VI Remax writing 3-line changes. They had something called include-db that added includes in the correct order source code as part of the make process, which made any IDE use impossible. And we said, we'd like to remove this because we want to use IDEs. They just looked at it as we like tentacles forehead again. So there was a lot of least common denominator. Sun had been very efficient. They had pushed out a Java every year until 2006, and then things started going south. So they had this testing that was doing black box testing done the wrong way. Huge overhead to check something in. Open source code reviews that basically just said, I don't like your variable name. They never said, I applied your patch. I tried some stuff. I found a race or something broke. No, it's I don't like your variable name. And to a certain extent, that's what happens if you do code reviews on mailing lists only, even today. Now, the language team uses Crucible, and we communicate better, but it's dangerous. It's hard to be a distributed team, much harder than being in the same room. Best part is being in the same room. Second best part is video conferencing. Third best part is phone, but it's starting to suck right now. And fourth is just email. That's horrible if you're on the same engineering team. So today, instead of taking 45 minutes to build the OpenJDK after downloading the components you need from the internet, you sync out the OpenJDK, you type configure, you type make images. 5 minutes later, you have OpenJDK images. We have white box testing for things like GC, etc. I mean, Frederick, who now works for Spotify, he considered this is a workplace environment hazard for me that makes me sick to go to work and have to build the OpenJDK like this. So I'm going to put my duties aside for 6 months and fix the damn build system, and it did, and he's a hero for that. So more and more of these things is happening. We're getting more and more resources and things like that. We have a really competent build and test infrastructure system in Stockholm who are doing good work. So it's always orders of magnitude harder and orders of magnitude more time consuming to retrofit good testing and infrastructure than to do it right from the start. So know and feel what QA means. And that's all I had to say today. Thank you.